All right, so our next presentation is by Dr. Manfred Laubichler from Arizona State University and Santa Fe Institute. Will be giving a talk on theoretical biology and history of biology. Dr. Manfred Laubichler is Global Futures Professor and President's Professor of Theoretical Biology and History of Biology. He's Director of the School of Complex Adaptive Systems and Decision Theater at Arizona State University. His work focuses on evolutionary novelties from genomes to knowledge systems, the structure of evolutionary theory, and the evolution of knowledge. His undergraduate training was in zoology, philosophy, and mathematics at the University of Vienna in Austria, and his graduate training was in biology at Yale and in history of science at Princeton. He's external professor at the Santa Fe Institute and visiting scholar at the Max Planck Institute for Geoanthropology in Jena, Germany, and external faculty member at the Complexity Science Hub, Vienna. Welcome, Dr. Manfred Laubichler. We're glad that you could join, and feel free to share your screen and your presentations, and the floor is yours.
Okay, thank you. Okay, so the best thing is I share my screen. That makes things easier. Okay, well, thanks, Yash, and thanks, Katie, for inviting me to this very intriguing and interesting event about what do we have in terms of data and models to better understand the human. You have focused a lot on various forms of genomic cellular atlas of the human. I'm stepping out and I'm placing the human into long coevolutionary dynamics and processes that led to our current condition of the Anthropocene. It is also based on a lot of data, and we could develop a formal mathematical theory on the dynamics of the Anthropocene based on a whole range of data sets, specifically about the so-called Great Acceleration over the last 80 years. But since it's an exponential curve, we have traced it back to about 8,000 years in the long tail. And those are data sets that were originally collected by the late Will Steffen and others. And you probably have all seen the famous tableau of the hockey stick curves of the Great Acceleration. So this is a core data set. We have added additional ones to it, but this is based on those data. What do we know about us and our time period, the Anthropocene? So that's the subject of that presentation. Now, this is predicated by the following quote by Walter Benjamin, inspired by the painting by Paul Klee, The Angel of History. And the basic premise here is that while we are inevitably projected and thrown into the future, our gaze is primarily focused on the past, which means we are actually flying blind into where we are going. And that is sort of a predicament of science, that we always are very good at analyzing and understanding the past, because that is where we can validate our models and theories, but we do not really pay equal attention, if we pay attention at all, about what the implications for the future are. This is a problem because we are now in a historically unique period of time that we have entered the Anthropocene. And the Anthropocene is basically a consequence of long coevolutionary dynamics that involve us within our environment and all kinds of other species, but that have enabled us to now shape and engineer the planet at global scales, which has led to the current condition that we are no longer in what is called a safe operating space. That means we have stretched a whole bunch of planetary boundaries to their limits, and we don't know what the consequences of those actions will be. We see already what some of those consequences will be, because we have a lot of challenges that introduce a whole new category of risk that is related to systemic risk as well as system failures. For those of you who want to know what systemic risks are, the most obvious definition is the insurance companies have a very successful and long history of assessing risk and putting a price on risk. This is what you pay for your insurance policy. And whenever the insurance companies stop offering a policy because they can no longer calculate what the costs or the risks would be, then you enter the domain of systemic risks and system failure. And for those living in the United States, you are aware that in many areas, you can no longer take out an insurance policy of your house because you are either in a hurricane zone or in a wildfire zone, and companies are leaving the market. So that's what we are talking about here with systemic risk. And in order to deal with all of that, we basically claim that we need a novel way of understanding these challenges. And I think that's how it fits into the topic of that 24-hour event, because it also requires us to organize different data sets and analyzing them. What are we talking about here in a longer term? We are basically talking about the deep history of evolved complexity as a story of major transitions in evolution. I've spent almost 40 years in thinking about those evolutionary transitions. And to make a long story short, there's a continuous history of evolution, adaptation, speciation, and it's interesting but boring. And then there are a few events in evolutionary history that are more interesting, and that is what we call a major transition, where there's a major reorganization of structures happening in the course of evolution. So examples are the origin of life, cellular life, multicellular life, so you get the picture. And if you analyze all those major transitions, you see that they share some common features. And that's where complex system science comes in, because it focuses on the shared commonalities across all those major transitions. They always involve changes to organization, to energy system, to knowledge and information flows in those systems, as well as material flows. So it's a structural transition in the system's properties. And another consequence is that when you have a major transition, you see emerging layers of complexity as well as novel feedback loops emerging, and that will become relevant in a moment. And our argument is that in the Anthropocene, the technosphere, sort of the totality of our built infrastructure that has emerged over the last 10,000 years, represents a major transition in evolution because it has all the properties of those major transitions. New organization, new energy system, new information flows, new material flows, and so on. So if you treat the technosphere as a major evolutionary transition, what are the consequences of this? Well, here's one. The technosphere basically is now being considered as a new sphere in the Earth system, along the more traditional ones as the lithosphere, the atmosphere, the biosphere, and so on. But and there are, of course, lots of interactions and feedbacks across all those spheres. The fascinating story is that if you look at the temporal components or the time scales, all the other ones have sort of overlapping time scales, which means that there are interesting cycles, such as the carbon cycle, the nitrogen cycle, that organize the dynamics of the Earth systems across those spheres. The technosphere is way off base because it operates on time scales smaller than a second, particularly when you think about financial markets and the like, and our new communication structures, which leads to the consequence that it's very difficult to imagine how we can establish traditional feedback loops that have sort of kept the Earth system in a dynamically stable equilibrium with the technosphere in the mix. Now, we talked about co-evolutionary changes, so a very brief excursion into evolutionary theory and its history. The argument basically is that standard evolutionary theory is not equipped to really address those challenges. This is sort of a brief representation of what we mean by standard evolutionary theory. We don't have to get into all the details. Suffice to say that there's exactly one feedback loop in there, namely that phenotypes interacting with their environment through natural selection and other processes basically change the composition of the hereditary material in the next generation. So that's the feedback loop. That's primarily the one that's characteristic of standard evolutionary theory. It says selection is the main feedback mechanism. There are some other features. So we don't have a constructive theory of the origin of variation that is outsourced to physics by saying, well, DNA is a very large molecule and we can actually calculate the average error rate, and that explains the problem of new variation. You reduce the description of evolution to changes in the sequence, in the frequency of alleles. And it has an implicit assumption of optimization, because that's what you get when you apply natural selection, and a very straightforward mathematical structure in terms of ordinary differential equation, as well as with all those theories like economics, like evolutionary theory, an implicit preference for equilibrium dynamics, because that's where the mathematics is trackable. Okay, now, in what our argument is that you need a different framework to understand those major transitions, including the technosphere. And again, I don't get into all the details, but as you see from this diagram, you have many more feedback loops within that conceptual framework. Because the important thing is that organisms or phenotypes are not just passively experiencing the selection pressure from the environment. They very actively construct their niches. They shape their environment, and that's already a feedback from the constructed niche, how it modifies selection pressure. But in addition, what we do to those niches has a direct feedback into the way our systems develop, into the development. We call that internalization 2 here, as well as to a lesser degree, directly into the hereditary system. I give you one example that is somewhat controversial, but provides a better understanding to what is currently a very hot societal topic. So we as humans, through our internal state, through our knowledge system, have over the last 250 years released literally millions of new chemical substances into the environment without thinking what the implications would be. This is basically how we change the chemical niche we live in. Now, there is one class of those substances called endocrine disruptors that mimic signaling pathways during normal development. So by changing the environment within which individuals, sort of fetuses, develop, and having substances in there that mess with the delicate balance of signaling, it's not surprising, so our argument, that we see a higher frequency of, shall we say, ambiguous gendered individuals. Because it's known in biology for a long time that sex is not really a black and white distinction, rather it's a continuum. And when we talk about biological organisms, the term is intersexes. There are all kinds of gradation of what sexual identity actually means. Now, we have, particularly over the last decades, released a lot of those endocrine disruptors. We are basically mammals in our development. That means our sex determination depends heavily on those signaling pathways. And so given the environment that those kids are growing up in, it is not surprising that you see a higher percentage of what's now called transsexual individuals. A simple biological mechanism, not at all an ideological, cultural explanation. That's just one example about what we mean by those various new forms of feedback mechanisms. So if we now apply extended evolutionary dynamics and abstract what the important elements are, that means that we have instead of in addition to the traditional form of evolutionary theory, different feedback loops. We have externalization. It's basically a niche construction in a very inclusive way, where our actions actively shape the environment and then that has effect on the underlying dynamics and feedback loops. And then internalization, that means how those constructed niches feed back on the operation of the underlying systems. Now, what that means in terms of distinguishing the extended evolutionary theory from standard evolutionary theory, that here we have an emphasis on the systems transformations as well as the multiple feedback mechanisms, that the developmental mechanisms are actually the explanation of the origin of variation, that we are dealing with evolutionary history and not just time, that we emphasize past dependency and construction, and that we need a more sophisticated mathematical representation that focuses on stochastic processes and non-equilibrium dynamics. So I'm definitely not getting into this, but we developed the mathematical framework for this, which in its most abstract way means that you can nest different temporal scale processes into each other, and you do it as a stochastic process framework where you make inferences about underlying mechanisms based on available time series data sets. So we are back to the need for lots of data about those kind of processes. And here we rely on either the kind of data that you're talking about in your Atlas project. So if you apply that to biological evolution, you would have time series data about gene expression during the sequence of development. You would have comparative data of gene expression across related organisms so that you get a picture about the evolutionary time scale. And we have developed a formal mathematical mechanism that allows to integrate those two types of temporal and more, if you want to, processes in a framework that allows to make inferences about underlying mechanisms. So that's the new mathematics. We can talk about that in Q&A if you are interested in. But that's what you need to do if you have if you want to realize what this new extended evolutionary theory can do. And crucially, again, to the context of the 24-hour event, what we need are very heavily curated data sets of time series at various scales related to human evolution and human activities. Okay, so again, a reminder where we are here and what we are talking about here. We are talking about the technosphere here in the middle as a major transition in evolution. Now, in order to understand this, now we are getting to the dynamics. We coined a term called the Anthropocene engine. And so we started analyzing the time series data of the Great Acceleration and developed a comprehensive mathematical approach and an underlying mechanism. And then we realized what drives that new mechanisms, what new feedback loops drive that new mechanism. And it's a closed feedback, positive feedback loop between population size, knowledge generation, and energy use. So it's pretty intuitive once you think about it. You need a certain number of people in those early agricultural societies that enable the division of labor and therefore set in motion the process of knowledge generation that is now reflected in science and technology, for instance. A major consequence of that knowledge generation is the better utilization of energy, which then allowed population to grow. And you see how this positive feedback loop can keep spinning and actually accelerating throughout the last 8,000 years. The interesting thing, anthropologically speaking, that this was facilitated by the first global act of niche construction, completely non-planned niche construction. because about 8,000 years ago, the underlying Earth system's dynamics would have been at the brink of introducing another cooling period, potentially another ice age. But this was stopped because globally, through human activities and particularly land use changes, there was a 50 ppm increase in the CO2 concentration over a short period of time. And that basically stabilized the long-term climate of the Holocene, stopping sort of those natural cycles from running their course. And that increase in the CO2 concentration is a consequence initially of deforestation. You know, our ancestors for their hunting practices used a lot of fire, which in Australia, North America, and other places eliminated a lot of the grown forests and put all the CO2 in the atmosphere. And once you had first instances of agriculture, particular rice agriculture in Southeast Asia, it was accompanied by methane emissions that also increased greenhouse gas levels to the degree that it stopped the cooling trend and stabilized the climate for the Holocene. So initial act of NITS construction enabling the Anthropocene engine as this positive feedback loop between population, knowledge generation, and energy use. So what is a consequence of all of this? The consequence is that while we were hunter-gatherers in small numbers, our natural daily metabolic rate was around 90 watts. Our current, what we call social metabolic rate, which is us and the technosphere per capita, is over 11,000 watts a day. So a 2 order of magnitude increase in our metabolic rate, that means our energy consumption. So to put this in the framework of scaling laws, what you have here is the standard scaling curve for metabolic rate, which scales to the power of 3/4. And what you see here is that 10,000 years ago, we were right where we're supposed to be between a mouse and an elephant. And now we are way off the chart because that's a log-log scale. So you can imagine if you plot this on a linear scale where we would be, you would need sort of the Empire State Building to find that data point. Okay, so that's the phenomenon. What is the explanation for this phenomenon? That's what our work is all about. So if you have a process of exponential growth, which actually drives all of that, in the Great Acceleration, you have a standard problem to deal with, that exponential growth inevitably will hit a singularity and a collapse point. And if you look into the historical record, humanity locally sometimes hit a collapse point, but globally we always escaped a total collapse because we came up with a new innovation that changed the dynamics. So we have that unbounded growth of the Anthropocene engine, or driven by the Anthropocene engine, through accelerating cycles of innovation to avoid collapse. And the question is, for the future, can we innovate our way out of that again? Or are we finally hitting a wall, not just metaphorically, but figuratively, and introducing a total systems collapse? That's the open question. And so for us then in our work about the dynamics of the Anthropocene, where we coined the term Anthropocene engine, the question then is, can we extend this framework to the socioeconomic dynamic and evolution of the entire planet, considering it as an integrated network of complex adaptive systems in the Anthropocene? So we have done a lot. We have about 5 papers in various stages of completion of all the different dimensions of this problem. So this is basically what we found, a couple of things. So in traditional scaling theory, Metabolic scaling is so-called sublinear scaling. That means that the scaling coefficient is smaller than 1, often around 3/4. Applying scaling theory to cities, using cities as a form of an organism, they found that cities have metabolic scaling in terms of energy, waste, and other elements of a city that is more or less consistent with metabolic scaling, but that cities have a so-called superlinear scaling coefficient when it comes to consequences of social interactions, such as innovation or crime, and they generally scale at about 1.15. And there is an upper limit with this type of social network approach. If it would be a completely connected network, the scaling coefficient would be 2. Now, what we found when we analyzed the data sets of the Great Acceleration is that we found completely new scaling regimes, such as if you look at GDP, which scales at right now at 2.1, and there are even higher ones in that data set. So that means that in the Anthropocene, enabled by the Anthropocene engine, we find completely new dynamical regimes as expressed by their scaling coefficient. So the biological scaling centered around the concept of how do we understand the metabolic rate as it relates to organism size. That is a very fascinating dynamic because this is what you have seen already. It scales to the power of 3/4, and it holds true in this case for all vertebrates from mouse to elephant, with the following average metabolic scaling rate. And so what goes into the biological rate? It basically is the base metabolic rate, that is the energy that you need to maintain your state, so supports all activity, and if you would be resting, and then if you're active, you get the active metabolic rate, and it's about 2 to 3 times higher. So if you measure your with some kind of Apple Watch or Fitbit, your daily activities, if you would just be lying in bed doing nothing, you would have a certain amount of calories burned. If you walk around, that is obviously higher. That's the difference between base and active metabolic rate. So, and then, so you can basically see that the active metabolic rate follows the same scaling, but just has a different exponent. Okay. Now, for modern humans, the active metabolic rate is not just what we consume as biological individuals, but also the energy needed to maintain our technosphere, or proportionally the components of the technosphere that we use on a daily rate that enables us, for instance, to have those 24-hour science event here. Because it's all the computational infrastructure and the energy used to maintain that. So it's the rate in the broadest sense in order to maintain the socioeconomic system, including all the infrastructure and individual in its present state. But also then with every metabolic rate, part of it goes into growing and developing new infrastructure. In biological terms, that means the energy needed to have offspring. In social metabolic rate, it's the energy needed to have offspring plus the infrastructure that comes with any new individual that we add to the global population. So that's the analogy how we look at what we currently see in the technosphere as an extension of what we understand how the biosphere works. So that gives us then the modern socioeconomic human that needs to be explained. And we looked at that already, the 90 watts to the 11,000 watts. Just to put it in perspective, every one of us is the equivalent of a 30,000 kilogram gorilla if you turn it into weight. So the King Kong movie was sort of appropriate, and that it played out in New York with a lot of infrastructure here. Or if you want another analogy, 12 elephants. And you see already the problem that is emerging in some places in Africa where the elephant populations are growing again and what havoc they reach. Now, if you think about that every one of us is 12 elephants, you see some of the problems. So with this framework of looking at the social metabolic rate as maintenance plus growth, we could then, and borrowing sort of that idea of an extended individual, so that we are not just us as biological individuals, but us as biological individuals plus all of our technosphere components, we could then write down a growth equation. And again, I don't want to get into this in detail here because it's just showing off that we actually did all the mathematics and have a formal theory that is very elegant. But you can derive this and do certain consequences and driving it to the Anthropocene equation that basically reduces to this form where the scaling coefficient beta has the following structure. And the problem that this equation has is then depending on how we structure the internal system dynamics, this one currently leads to continuous exponential growth. This is what we see if you look at all the data sets of the Great Acceleration. The trick would be the following. In biological organisms, if you look at the growth rate during development, so when you start dividing from the fertilized egg, 2 cells, 4 cells, initially the growth of any biological system is also an exponential growth curve. But it then reaches a tipping point where it stops growing. And that's where sublinear scaling or bounded growth emerges. And if you ask how that is possible, from a mechanistic point of view, it's basically that at some point in the development, negative feedback loops kick in. For instance, take the development of the nervous system or the brain. So cells keep growing, and then then all of a sudden a mechanism of apoptosis sets in. That means selectively different cells keep dying. And so if you look at any biological organisms, here the rat, you have this exponential phase, and you then flatten out and you reach a dynamically stable state, where basically you have roughly the same amount of cells and you have replacement of those cells that die, but you no longer have exponential growth of cells in your body. And a lot of that is regulated by negative feedback mechanisms. In the technosphere, where we have this superlinear metabolic rate, often very, very high, particularly in the financial sector, we do not have those, as of yet, those negative feedback mechanisms that would lead to bounded growth. We have open-ended growth. And that means we are approaching a singularity, right? And the question is when. And so if you look at population growth, this is a projection that pretty much tells you what we mean by a singularity. Although in population growth, we are beginning to see the emergence of a plateau because there are the equivalent of those regulatory negative feedback mechanisms. A lot have to do with the educational attainment of women in different societies and things like that. So here on the population level, we actually see that this is not necessarily going up continuously, but it's already about to approach a plateau. But if you look at, this is sort of populations where we currently are not quite there yet, because depending on where you are, they are still in an exponential phase. And if you look at all those hockey stick curves, this is the famous Stefan diagram, there you see the majority of them keep growing. Those who have limitations, such as domesticated land, reach a plateau. But those that have to do with energy and technology and financial systems are in a completely unbounded growth phase. So if you, this is now again some of the former theory that we developed, if you have a system that has unbounded exponential growth, what you can do is basically you can calculate the finite time singularity. And you can calculate when it actually happens. So super an exponential growth will lead to collapse. Question is when. We have already seen that what we have done historically, we found an innovation, often an innovation in the energy system that got us out of the impending collapse. Okay, this is something else. And so there is a sequence, what we call of singularities. So this is the time of a paradigm shift. And we are going back into placing that into the long-term evolutionary history. And so you see that the paradigm shift time gets shorter and shorter as we now enter into the technosphere. And so again, you can do some fancy math and you can figure out what the approach to the singularity is. And then you can try to make predictions as to, given the current dynamics, as if nothing would change, when would we hit the singularity point? And when we did that, for many of using the data sets of the Great Acceleration data set, for many of the examples, the singularity initially we thought would be around 2035 to 2040. Then we realized that even though that looks very much already a good fit with the data, there is indeed a breaking point in the time series in the mid-70s. So if you then divide the time series into two, then for many cases, the singularity point shifts. And it is now roughly around 2070 that most of the systems would collapse under current conditions. Now, that breaking point in the time series was actually something very interesting for us to find because we did this just with data and mathematics. And when we said, well, something must have happened that is of interest in the mid-1970s, and we started talking to historians, then they got very excited. And now everybody has their favorite story as to what exactly shifted dramatically in the historical dynamics in the mid-70s. And from the financial system, it's the end of Bretton Woods and the gold standard that unleashed the whole current financial system that we have with its hyper-exponential growth. There are cultural shifts. There are shifts in technology, such as the real beginning of the spread of the PC revolution. So everybody has their famous story. So you can think about what you think about was so important about the mid-1970s. But for us, this was a very important confirmation because we have not looked at any bias as to what we think is a historical meaningful change. We just looked at the data and we found that breaking point in the mid-1970s. So so speculations. Everybody invited to come up with their own best example for what happened in the 1970s. So if you look at this as the phenotype of the great acceleration of the Anthropocene, we find that breaking point. And here just some data about what happened and where the new TC sort of the collapse point is. And you see for the majority of data sets, it now is in the 2070s. There are a few that might collapse earlier, according to that analysis. Okay, so what's next? So far we have looked at this dynamic on a global scale, because that's where the easy data points were. Now the challenge for what we are talking about here, organizing atlases and data sets. What we would like to do is have a higher geographic resolution so that we can basically identify those dynamics at a more regional scale. Beginning some work with a colleague in Jena, Jonathan Donges, but here the data collection is challenging. But it is something, if you have a framework, and as Katie was saying before, in generalize that, if you have a platform to systematically collect and store all those data and then make it accessible, we probably can fill in a lot of those gaps that we currently have for this type of regionally specific analysis. Another one is doing it more fine-grained into deeper historical time. Again, a big data challenge. We have done it, and this is work that I'm doing together with a colleague also in Jena, Jochen Büttner, where we have extended time series such as population numbers and CO2 emissions over time, which, if you just compare it, looks very interesting. But if you apply a scaling framework to it, you find a few relevant breaking points. So you find different regimes, such as from the 1790s to the mid 19th century. Then there's the huge period of the real taking off of the Industrial Revolution. Then you have, with the various crises around 1870, you have another different regime. World War I does a reset. Great Depression does a reset. Then World War II doesn't do much. Then it goes to the oil price shock, and then we have a regime that characterizes us until recently. So really understanding those historical inflection points also requires a better data collection and data organization. Now, again, we can tell a good historical story about what went on around each of those breaking points in the dynamic, but they were established simply by analyzing the data within our overarching formal framework. So it's a nice confluence between data analysis and underlying modeling, and then combining it with historical contextualization. Yeah, there's another one that we can do. You could actually see certain shifts about what the main energy sources used actually were, and what that diagram tells you, and this is an important lesson to be learned for any discussions about energy transitions, and you can extend that all the way back 3.8 billion years in evolutionary time. Generally, with any energy transition, the old energy sources don't go away. You just add a more complex mix. And that's an important thing to keep in mind when we talk about changing the energy system today. So what are some of the crucial observations to come to a conclusion here? So in general, we know that all complex systems are governed by regulatory structures. This is a general insight from complex system science. We also know that complex systems construct their own niches, and we talked about that in the beginning, that through that act of niche construction, new forms of feedback are introduced into those systems. And as a consequence, dynamically stable systems have the right kind of balance between positive and negative feedback loops, as we have seen when we looked at the metabolic curve of biological organisms, where you have bounded growth. So those are general insights from complex system science and evolutionary theory. What does this mean for us? As we have seen with the story that I told you about the Anthropocene equation, that starting with the Neolithic, humans began to eliminate negative feedback that regulated their growth. That closed that positive feedback loop, sort of the Anthropocene engine, the feedback loop between population, knowledge, and energy. And that has been closed for the last 8,000 years. And that has led to the continuous acceleration in human history, as well as sort of the emancipation of humans from their natural environment and the increasing reliance on what we call the technosphere. And sort of the current planetary crisis can be seen as the culmination of these longue durée trends. So what can be done? Well, the general guideline would be we have to introduce negative feedback into the system. That's a nice statement, but what does that mean? So traditionally, you could say negative feedback could be, well, we can start killing each other, which we are doing to some degree and seem to accelerate these days. But that's not really the solution that we want. So negative feedback in the context of human and cultural social evolution needs to come in form of values, norms, and regulations that make up sort of a social regulatory system of humanity that can take the same function as the various feedback loops that exist in the biospheres that sort of maintain dynamically stable ecosystems, for instance. But we have to do it on the level of our social norms. And there are different types of regulation. And currently, we see the complete failure of a model that sort of extends a hierarchy from communities to nation states, and nation states being the most central actors. And then you have sort of organizations of nation states, such as the UN. And that doesn't seem to work. You only have to look at the annual circus of COP that doesn't produce anything of substance. Because at the level of the politics and the game theoretical relationships between nation state, that has never yielded anything productive. So the alternative might be to derive those regulatory systems out of the concept of a global civil society or a global commons. And so, this is sort of a link between Indiana University and ASU is sort of Elinor Ostrom. So the end of her life was in both institutions. And she really worried a lot about the feasibility of a global commons after she demonstrated that on a local scale, that actually can work, that you have those values and norms that lead to a bounded growth of societies. But can that happen on a global scale? That was, by the time she died, an open question and still is an open question. Another question is the role of scientific knowledge. So obviously we have a lot of the data and the insights, but we seem to be completely incapable of making use of them in order to advance solutions. And so something that needs to be further developed. And that means we need more integrative and transdisciplinary forms of knowledge. So far I have told you one side of my daily life, namely as the director of the School of Complex Adaptive Systems and a member of the Santa Fe Institute. Now, in the last minute, I give you sort of a perspective of how we can actually potentially translate that knowledge into action. And that is the decision theater that we have at ASU, which is a facility that brings together data visualization, modeling, scientifically based scenarios with facilitated processes of decision making. That means you bring the stakeholders and the decision makers into our facility, or you go to them, and to try to show them the consequences of certain actions. And we have over 100 completed projects, and all I can say is that it works under the right circumstances, and that it can be a way of translating data, visualizations, and database scenarios in support of decision making. And so our project range from the education system, economic transformation, energy systems, water systems, regional transformations, you name it, and have been pretty successful at a admittedly still very small and local scale. So what we are trying to find ways to scale that framework of decision theater so that it is more broadly applicable. This is sort of different types of events with the decision theater. It is a very effective way of trying to come to solution. So with that, I thank you, and I think I still have left some time for questions.
Thank you very much. This was like an amazing talk and completely outside of my domain. So this was super interesting for me. And yeah, the floor is open to questions now. I'm sure Dan and Kari and Andy have a lot.
Manfred, a true pleasure. Thank you so much for presenting this. And I'm absolutely a true believer that we need to bring in all of the different intelligences to the table, human and otherwise machine intelligence, to solve some of these challenges. And it's great that there are some brave individuals that present in front of very different audiences, right? And listen to others from very different audiences, like what Yash just mentioned. We must be able to do that. And this is also what this event is trying to accomplish. I very much appreciated the reference to Lynn Ostrom's work here at Indiana University. She was the first lady to win a Nobel laureate in economics for her work on the commons, and how we can get there, how we can overcome the selfish genes and think for all of us, for this planet, the only planet we have so far. And so I wonder what you have found with the decision theater. I know we have some of the visualization experts here on the call. They're coming in to the next panel, so they will also come in as we are discussing this. And I would love to understand what has happened with the decision theater so far and how others can use them, and how we can use data visualization to overcome some of these boundaries that exist and miscommunication elements, and how we get the better dialogue with those that have the data, those which want to use the data, not just for researchers, but also for policymakers up to the highest levels, and ultimately also to the next generation.
Yeah, thank you, Katie. So the decision theater is basically an organization that connects to many of the expertises and interests represented by this event. So one of its premise is that in order to make informed decision, we need evidence-based decision-making. Now, evidence-based decision-making often takes the form of some experts testifying somewhere or somebody writing a report that doesn't really connect. So the decision theater approach is highly interactive, and it depends crucially on very elaborate facilitation. So everybody who wants to participate in that, and as I said, we have over 100 projects completed and currently about 30 that we actively are pursuing. And it has to do with stakeholders and decision makers at different scales. So take, for instance, a scale that we are all familiar with, sort of a more localized, sort of from county to state government in the United States. So if they come to us with a problem, or if we co-define a problem, the first step is that we don't assume we know what the problem is. So you have to listen to a diverse group of stakeholders, and you begin without any visualization. You begin to sort of try to map out what the challenge really is in all its dimensions. At the next step, and this is subject to change through iterations, but at the next step, once you have sort of sketched out the problem, then you begin to ask the question, what data do exist and what data do we need to actually say something meaningful about that problem? And that often actually leads to very surprisingly positive results, that people who have data and are not necessarily inclined to share them are willing to share them when they see for what they will be used. So then we sort of begin data analysis, data visualization. just to put things in perspective, I have currently a team of 60 in the decision theater. Roughly 15 are data scientists. And another 5 have to do with UX, UI, because you need to present that in a way that actually is meaningful and can be communicated. But once you have the data, then you have sort of a next round where you use the data to explore the current state of the system or the current state of the problem. And then you begin to, and it's all overlapping, you begin to find or sometimes adapt and develop dynamical models of system transformation. And they are designed that they actually have intervention points that can represent a decision that somebody can make. But then it allows us to create scenarios based on the data and based on the models and those intervention points. And when you do that, and since you have different perspectives represented in the room, and you have seven screen display environment, a lot of fancy technology, then you can highlight different consequences. So what you can then visualize is if a decision is very good for one group, but pretty much a disaster to another group, it becomes visible. And then they can negotiate. And we have had a lot of success over the years because if you do this right as a facilitation and you explain, look, all those problems we are talking about, they do not have an optimum solution. So you have to find a mutually agreeable solution. And it generally works if the willingness of the participants and the trust is there. And that's what you have to establish in that process of iterative engagements.
Mhm. Yeah, I put a number of links in the chat. The last one is a participatory global simulation, which came out in 1993. I mean, this is a long line of ambition and work that has been making steadily progress. But I think it's hard for most to understand formulas. I think having something in a very concrete, visually rendered way, like a loudness in a city, for instance, that people have to put up with, and then how do you divert traffic so that everybody still can reach the places they need to go to, but at the same time also can live their life in a quiet way. It's not easy to do these decision theaters, and it's really cool to see that you're working on this, and I would love to learn more.
Yes, and we have to find a time for you to visit, as you know.
I do have
Let's do that over the next couple of days.
I have one more question for you,
Yes.
Manfred. So you were showing earlier visualizations, or you're making points about humanity's evolution, at a certain point, eliminate negative feedback, putting in positive feedback. But much of human history is basically without any data. And I'm curious, which point of human history do you think is like, for which point of human history do we still have that's long ago? Do we still have enough data to model what specific systems look like at the time?
Well, it might come as no surprise to you that I work a lot with archaeologists. And we increasingly find data points, not necessarily on a global scale. So those are basically for local societies, where I would say the last 30 years or so have seen rather substantial transformation in archaeology, particularly also because that's around the time where archaeologists began to collaborate with modelers. And so that informed the way they looked at their collections and looked at their data points. And then there are now, new technologies, LiDAR observations from space, where you can sort of map out, for instance, the actual scale of ancient cities that wasn't easily possible when you just start digging, and also allowed to map road networks and things like that. So nothing perfect, but I think we are getting to the point that the models that we might propose can actually be tested with all the caveats that it's not like a laboratory experiment and things like that, but they can be tested accurately enough so that we can get some of those things. So we just yesterday got a paper accepted in Nature Cities, where we applied this framework of scaling analysis to monuments throughout the Roman Empire, as well as the presence of monuments being billionaires putting a name on a football stadium and things like that. And the interesting thing is that the scaling relationships are pretty similar, and so is the Gini coefficient of social inequality. So it's not yet a causal model, but it's a very suggested data set that you can analyze and can say, well, there might be something in the dynamics of societies. If they have a certain degree of inequality, then there is a tendency of the oligarchs to present their power in terms of monuments. It's a tiny little piece, but it just shows that you can get data points that allow you to build analysis and models that go in that direction.
Thank you.
Thank you. I think we are at 8 o'clock. Thank you, Yash. Thank you, Dan. Thank you, Manfred. Looking forward to this discussion in the future.
Yes.